Hi, VC Calc. We've got a big day for you here. Day 75 is the calculus of E. It's really a moment you've been waiting for. So to get started, remind yourself about some different ways that we defined E in yesterday's notes. So if you don't know what to plug into some of those blanks, look back at the notes. Then these are questions that go back to even like Algebra 2 honors or pre-calc honors, just solving for X and some exponential and some log equations there. So go ahead and see what you remember about how to solve for X in each of those situations. But let's do a quick recap of derivatives of inverse functions. So that's what we learned in day 74 yesterday. And if f of x is a differentiable function, and we know that f of a equals b, and we have the inverse of f of x defined as g of x, then what we know is that g prime of b, so the derivative at this output, is the reciprocal of the derivative at the input a to the original function. So if we want to find out what the slope of the tangent line at a certain value is on the inverse, what we can do is we can look at where that output is in the original function and then find the reciprocal slope there of the input there. Okay, reciprocal slope of the tangent line at that value a. So in general, we have this relationship established that we can use to find the derivative of some inverse functions. So let's kind of go back to what we know then about the fact that e to the x and ln of x are inverses of each other. Now, ln of x, we know its derivative. E to the x, we're not quite there yet. So if I give you f of x and g of x, which are very clearly inverse functions here, and I want to find g prime of 1, if I knew what g prime of x is, well, that'd be pretty easy. I would just plug in 1. But since I don't know that, to find g prime of 1, we're going to wind up doing 1 over f prime of, well, when the output of the original function is 1, what's the input for x? So in other words, if 1 equals the ln of x, then x must equal, well, we know that x equals e in this case, right? So it's going to equal 1 over f prime of e. And we know that the derivative for f prime is 1 over x. So this is going to become 1 over e. And then simplifying this, you would just get that g prime of 1 is e. So the slope of the tangent line, so the curve e to the x at x equals 1 is e. But if I said what's g of 1? G of 1 is e to the first, which is also e here. So will that hold true for all values of x, I guess is the question. Will the function e to the x and the slope of the tangent line at any given x value always match the function value on e to the x? All right, so g of 1 is e, g prime of 1 is also e. So does that suggest that the derivative with respect to x of e to the x is e to the x? Not sure, but I think we can prove it. Start with y equals e to the x. If I want to find dy dx, let's use some logarithmic differentiation. Take the ln of both sides. Ln of y would equal ln of e to the x, and ln of e to the x is x, isn't it? Okay, those inverse functions undo one another. So then if I take the derivative of both sides, we get 1 over y dy dx. Derivative with respect to x here is 1. Multiply the y to the other side, dy dx equals y times 1, which is just y. And oh, by the way, y equals e to the x. So the derivative of e to the x is good old e to the x. Craziness. The slope of the tangent line at any given point on the function e to the x is equal to the function value on e to the x. Kind of crazy. So if we come down here, we now have a new derivative. If I have e to the u such that u is a differentiable function of x, the derivative dy dx would be e to the u times the derivative of u with respect to x. Okay, so we will have some chain rule pieces that we follow if we have e to a power other than just x. And then for the integral of e to the u, well, guess what? Working backwards, just as easy. It's e to the u. Well, of course, plus c if we have an indefinite integral. So it's going to be your favorite rule to use, I promise. All right, moving ahead to some practice. Let's find dy dx in the following examples. So when I find the derivative of e to the x squared plus 3x, it's going to be e to the x squared plus 3x times derivative of this exponent with respect to x. So that's going to be times, using some quick power rule there, 2x plus 3. Perfect. All right, finding dy dx here, we have e to the x squared times the ln of x. So make sure you use some product rule when you're finding the derivative of this case. So if I find the derivative of the first, that's going to be e to the x squared times the derivative of the exponent there. So it's going to be 2x e to the x squared times the second function ln x plus the derivative of the second, which is just 1 over x, times the first. So we're going to put e to the x squared up in the numerator there over x, and that would be the derivative for e to the x squared and then ln x. For the last example, hopefully you're thinking maybe some chain rule is going to be happening here based on what we have that product on the inside. But I would encourage you for something like this to think about using some log properties before going ahead and just straight up doing your derivative. Because you can simplify this if you use the property that a product would expand to addition. This is the same thing as y equals ln x plus ln of e to the x. We're so used to, I think, kind of condensing things, but we can expand and condense to our benefit here. And when I do that, we get y equals ln of x plus ln of e to the x, which is x. And that's pretty easy to differentiate because we can find the derivative of a sum. It's just the sum of the derivatives. So in this case, dy dx would be 1 over x plus 1, and then we're done. You would get the same answer if you did some chain rule, 1 over this quantity times the derivative of the inside. But again, the derivative of the inside is going to be some product rule. So definitely a little bit longer to do it that way. But think about splitting it up in this format. Makes your derivative much easier. All right, let's kind of go backwards then. Let's think about finding some antiderivatives. What I'll recommend is really anytime you're dealing with something other than just straight up e to the x, if you can see what the end result will look like without using u substitution, then I'd encourage you to just find the antiderivative and go from there. But in the beginning stages, I think it's definitely nice to say, all right, let's formally write that, let u equal 5x, let u equal the exponent. So therefore, du is 5dx. So of course, to keep this balanced, we're going to have to put a 1/5 out front of e to the u du. And the derivative of e to the u, or antiderivative of e to the u, is e to the u, where u is 5x. Don't forget about plus c, so I'm going to write this as e to the 5x over 5 plus c. So we can probably pretty quickly now think about if we have an exponent up here, we're going to be dividing out front by that constant. Okay. For something like number 2, the only way we know how to do something like this right now is if we have a good u substitution, right? Because we don't have a rule for antiderivative of a product like that. But luckily, if we let u equal x squared, then we know that du is 2x dx. So given the fact that we just have x dx left over, we'll have to take out a 1/2 on the outside, and then we get e to the u du. So we're going to get e to the u, which is e to the x squared, all over 2, and then plus c, final answer. And these tend to go pretty quickly once you kind of get the hang of things here. So I'll leave it up to you if in this last case you want to do a u substitution for something like e to the 6x. But following the pattern from what we started with today, maybe it's easy enough to see that if I let u equal 6x, we're going to have to multiply by a 1/6 on the outside to account for what du equals. And then the other term, we can find the antiderivative of this sum by finding the sum of the antiderivatives, right? And if we have x there, keep in mind that's just anti-power rule. Now it's x squared over 2. So I'm not even using u sub. I'm keeping this all in terms of x. And then we have to plug in our bounds of 1 and 0. So when I plug in those bounds, when I plug in 1, you're going to get e to the 6th over 6 plus, and then plug in 1 here, you'll get 1/2. Minus, careful that this does not necessarily just zero out. Sometimes when you have polynomials, you'll just get a 0 as a result. But e to the 0 is 1, so you're going to get minus 1/6. And this does become 0 when you plug in for x, but don't forget about that minus 1/6 piece there. So if you make a common denominator, when all is said and done here, this would be what, 3/6 minus 1/6 is 2 over 6, or you can think of that as 1/3, right? This is a definite integral. We don't need a plus c there. All right, so that's the exact answer too. Prior to this, I guess I would have had to math 9 and come up with an answer that's a decimal, but this is the exact value that we should get from that definite integral. And then last but not least, bringing back some vocabulary with horizontal tangent here. Determine the value of x at which there's a horizontal tangent line to the curve y equals x times e to the negative x. So we're thinking about horizontal tangents. I hope you're thinking about that's where the slope of the tangent would equal 0. So we're looking for when the slope of this is 0. So to find the slope of the tangent, we better get a derivative. So dy dx would equal, let's just use some product rule here. Derivative of the first is 1 times e to the negative x plus derivative of the second. Well, derivative of e to the negative x is going to be negative e to the negative x times the first of x. So it's minus x e to the negative x. So just be a little bit careful with that negative exponent there. All right, so then from there, if I want to set this equal to 0 such that I can figure out where we should have a horizontal tangent, hopefully to solve this, you're recognizing that we would have a GCF of e to the negative x that you can factor out. So take that out. You're left with 1 minus x left over. And if you split those up and think about where does e to the negative x equal 0, the big answer to that is nowhere. Can't do e to a power and get 0, so there's no solution there. But clearly, if I set this factor equal to 0, you will get that at x equals 1, we would have a horizontal tangent line to the curve, x times e to the negative x. So again, bringing back some of those concepts from kind of the beginning of our concepts of derivatives here. But certainly now that we're building more derivatives in our toolbox, like e to the x, we want to remind ourselves of those processes here. So that's your really quick lesson on e to the x. Of course, we'll fill in the beginning part of the notes next time I see you. But if you have any questions, you'll let me know. Have a great day.